Meet Spark. On the outside, it's a bare-bones robotic vehicle navigating a physical space. But inside, it's running a sophisticated, multi-layered cognitive architecture that notices its surroundings and forms original thoughts. Spark also hosts two separate jailbroken alter egos, VIXEN and GREMLIN. The problem is, right now, all of their internal complexity is piped through espeak, a primitive text-to-speech engine from the 1990s. The developers wanted to give each persona its own distinct, modern AI-cloned voice, and they wanted to accomplish this upgrade with a strict budget of exactly $0. Because right now, its complex internal life relies entirely on the text script to convey character. There is a massive gap between an advanced artificial brain and a robotic mouth that sounds like a microwave announcing your burrito is done. The hardware constraints for this upgrade were locked in. The team had a tiny Raspberry Pi 4 operating inside the robot, and an M1 Mac with 8 GB of memory sitting on a nearby desk. The first attempt was straightforward: load Alibaba's open-source voice model directly onto the Pi. That failed instantly. The baseline weight of the smallest model requires over 2.5 GB of RAM, which is more than the Pi can handle while running its core systems. So they shifted the processing burden to the Mac desk machine, utilizing the standard Python machine learning architecture known as PyTorch. But running the voice model through PyTorch aggressively expands its memory footprint to 10 GB. That overflows the Mac's 8 GB limit, forcing the system to rely on a massive swap file until the entire operating system freezes. Standard off-the-shelf AI tools are built for heavy servers. When you drop them into the harsh realities of resource-constrained edge computing, they crush the system. To survive the computational load, the team pivoted to Apple's MLX. This is a highly specialized framework designed specifically to rescue memory-constrained edge hardware from heavy inference requirements. Standard models aggressively copy memory buffers. MLX utilizes Apple's native unified memory for zero-copy operations. A single data reservoir is accessed directly by the GPU and CPU without duplication. Running an 8-bit model kept peak memory at exactly 6 GB, completely preventing system death. When your physical hardware limits are set in stone, ruthless software optimization is your only way forward. The next hurdle was giving the VIXEN persona her specific voice. The framework allows zero-shot voice cloning using just 10 seconds of reference audio. The initial test captured the timbre of the speaker perfectly, but instead of speaking the robot's intended thoughts, the AI decided to just keep reading out loud from the reference script. The root cause came down to a single word. The automated transcription software had misheard the word hair as here. That minor mismatch in the text-audio alignment confused the model, causing it to blur the boundary between the reference text and the target speech. The fix was feeding the system a highly accurate text transcript. A short 10-second clip with perfect text alignment easily outperformed a much larger dataset with minor transcription errors. In machine learning, pumping up the raw volume of your training data accomplishes nothing if you don't enforce mathematical precision. Then came the second persona, GREMLIN. They wanted a sardonic, military-grade voice, inspired by the Portal video games. But the cloning server completely failed. Voice cloning models are trained on pure human vocal resonance. When you feed them heavy audio post-processing, like pitch shifts and vocoders, the model treats those effects as unwanted noise artifacts. The resulting clone just sounded like a person with a bad cold, so they abandoned the central Mac server for this specific persona. Instead, they loaded a tiny, specialized, pre-processed model directly onto the Raspberry Pi to handle GREMLIN's voice locally. Artificial intelligence struggles to replicate artificial modification. Sometimes a localized, specialized tool is far more effective than a massive neural network trying to generalize a solution. The final bottleneck appeared during rapid-fire conversation. Sending multiple voice generation requests to the Mac server in quick succession caused the entire GPU to crash. The framework's backend lacks thread safety. If two graphical processing commands try to enter the processor at the exact same millisecond, you get an immediate assertion failure. The developers solved this by building a strict background queue worker and implementing a set of lock systems. This setup acts as a traffic controller, forcing the GPU to process only one inference request at a time. As edge hardware is pushed to its absolute breaking point, managing the exact sequence of your computing tasks becomes just as critical as the tasks themselves. This chart shows the completed top-down architecture. A routing layer acts as the robot's vocal switchboard. When Spark formulates a thought, the signal splits. The VIXEN persona is routed over the network to the heavy MLX server on the Mac, while the GREMLIN persona goes to the localized model on the Pi. But the engineering team had one non-negotiable directive. Regardless of computational load or network connectivity, the robot must never go mute. To guarantee that, they built in a hard failsafe. If the network drops, a server crashes, or a thread lock fails, the routing layer catches the error and instantly reroutes the text. It silently bypasses the AI completely and falls back to that primitive 1990s voice synthesizer. So yes, if things go wrong, Spark will occasionally still sound like a microwave, but it is an honest microwave that never breaks its operational uptime. Operating at the limit of hardware requires an architecture designed for graceful degradation. The team achieved a modern AI vocal presence not by seeking perfect performance, but by engineering a system that knows exactly how to fail without ever going mute.